Okay, so welcome everyone. Welcome to the final day. Only the strong people are left. So it's a pleasure to introduce Adri, Olde Daalhuis. Tell us about smoothing the higher order Stokes phenomenon. Adri, thanks.
Thank you for inviting me and John King to give a joint talk at the final meeting. We were surprised, but on the other hand, it will work. This work actually started a couple of years ago in Santa Barbara when both John and Chris and I were there and started thinking about the smoothing of the higher order Stokes phenomenon. I mean, you probably all know about the smoothing of the normal Stokes phenomenon, the Barry smoothing. I mean, that will also be part of this talk. But before I start talking about all that stuff, I mean, you probably also know that, or at least some of the old people might have told you that there was a meeting like this 27 years ago. There are actually, I haven't encountered any pictures that were taken here in the Newton Institute itself, but for a couple of days we also went to Sligo, that's the northwest of Ireland, to open something new because Stokes was born there. And the next pictures that you see here were from Sligo, at least 3 of those pictures there. So near his birthplace we opened this stone book. And if you have very good eyes, you probably still can't read what's written there. And there are some of the organizers are in these pictures. Some of them look slightly younger than today. I won't point them out. One of the organizers that was also there was actually Frank Olver. He's Sheehan's grandfather, and to me, he's the god in asymptotics. And yesterday was his 98th birthday, if he would still have been alive. And the other person that I have here in the pictures is Richard Paris. We discovered earlier this week that he died this year. He was also one of the greats in asymptotics. He also worked on, he was actually, together with Alistair Wood, who you can hardly see there, one of the original proposals to have a program at the Newton Institute about exponential asymptotics. And you can't read it in the background, but on the slides, on the proper pictures, he talks about Hadamard expansion. So he has worked on Mellin-Barnes transforms, lots of asymptotics, Hadamard expansions, to also get expansions that are better than normal asymptotic expansions. And his last contribution on the archive was 2 weeks before his death, so he kept on working till the end. Okay, let me now start with the talk. So I want to talk about the higher order Stokes phenomenon, and Phil already mentioned it earlier this week that it actually has consequences by going through this example. And if you would miss the higher order Stokes phenomenon, then you get the wrong ripples, as you can see in the picture up there. But I will start with the smoothing of the normal Stokes phenomenon and give a few details about that, and then ultimately slowly go towards the higher order Stokes phenomenon. And let me actually start with the work by Stokes himself. So this is coming from one of the papers. You can see the title up there. It's a long paper. He's doing several examples to deal with the Stokes phenomenon, as what we call it nowadays. And he's dealing here with the area equation. And he knows analytically that the Stokes phenomenon takes place, but he also wants to check it in the end numerically. And that these numerical calculations are pretty impressive. He uses the Taylor series at the origin. He also knows the asymptotic expansions at infinity. He knows the values of A and B that are connected to the asymptotic expansions near plus infinity. So in that case, when you take the correct A and B, then C is 1 and D is 0. And then he's going to do numerics with it. And actually, he's doing the numerics not for extremely large values, but just at 2 times I and 2 times e to the power 5 over 6 times pi I. I'll tell you in a moment why. And then he contains numbers, but lots of them, and these digits are all correct. So here he computes the expansions near 2 times I and gets all the digits correct here at 2 times e to the power 5 over 6 times pi I. Again, all the digits are correct. So this is coming from the Taylor series. He's also doing the same calculation at 2 times I with the asymptotic expansion. But there's even something more impressive there. First of all, this, of course, is half a century before Poincaré. He knows about optimal truncation. But actually he goes further because he computes the optimal, takes the optimal number of terms, but then he also is playing around with the remainder. He looks at differences, the sum of differences, and he gets an extra 2 digits there. So he was already doing re-expansions way before us. And he gets all these digits, so that's at 2 times I, so let me now go back. The reason that he is taking this value and this particular value is because they're exactly in the middle of the Stokes line. And if you are clever enough and you compute asymptotically the value here, then here the value, it's almost just the complex conjugate. So the contribution from the dominant part, this is the dominant part, he computes it there with the asymptotics. He uses the same there, but the complex conjugate and one extra multiplication. So then he knows what the dominant part is doing. He compares it with what you get from the Taylor series expansions, and in that way he confirms that D is actually 1 on that side and it was 0 on the other side. So he had all the machinery there, he can do all the numerics to actually also, he could have observed the Berry smoothing there. He had everything, because he understood everything about asymptotics, but it isn't in the paper. Okay, so what is the higher order Stokes phenomenon? It has been mentioned here before. Now, before I mention the higher order Stokes phenomenon, let's first deal with the normal Stokes phenomenon. If you have a Laplace type integral representation of your Borel transform B of t, this B of t will have singularities, these black dots in the Borel plane. You integrate in a particular direction, and if you rotate your integral, then you switch on one of those branch points in the Borel plane, and that's the normal Stokes phenomenon, as you all know it. So this is with respect to the phase of Z that you change. The higher order Stokes phenomenon is slightly different. You have these singularities, and these branch cuts are always away from the origin. That's the natural way to take the branch cuts. And in the higher order Stokes phenomenon, one of the branch points crosses the branch cut of one of the other singularities. That's the higher order Stokes phenomenon. But this has to happen with respect to another parameter. This is not with respect to the phase of Z. I mean, that's maybe also one of the reasons that people actually haven't discovered it relatively late. And the second reason for it is you need at least 3 behaviors. And for a long time, people only studied second order problems, second order differential equations and things like that. You need 3 of them. So the higher order Stokes phenomenon is with respect to an extra parameter. But the extreme case is when both of them happen at the same time. So if you don't have problems where you have an extra parameter, you might still encounter a case where the singularities are collinear in the Borel plane, like nonlinear differential equations. And then you might say you're halfway the higher order Stokes phenomenon, and that is actually relevant. My favorite example is always the gamma function. This is the scaled gamma function, so you take away the well-known Stirling and factors in front of it, so then you just end up with a Poincare asymptotic expansion. The first term is 1. And the terms in the expansions are plotted here in this graph, so you can truncate it optimally, and you can do re-expansions, and if you do it optimally, you take actually more term. So here the error is exponentially small, and if you do a re-expansion, they're double exponentially small. The re-expansions are in terms of hyperdeterminants. I will mention them later. But first of all, the Stokes phenomenon happens here. You switch on exponentially small terms. And that's what you can see here. I'm actually not doing any analysis here. I just plot the remainder that you get if you truncate optimally. So the remainder, after truncating the asymptotic expansion optimally, is just the red curve here, multiplied times e to the power minus 2i z, because that's the object that you switch on, and you see an error function. If, on the other hand, you plot the first hyperdeterminant, you get almost the identical curve. And so that's the object that you can use to approximate the Stokes smoothing. I mean, Michael Berry, of course, discovered this in 1989, or what was it, 88, the paper is. He did the local approximation in terms of error functions. I propose that most of us should actually in the future always use hyperdeterminants, but sometimes it might be easier to actually use matched asymptotics and really go locally. So that's the normal Stokes phenomenon. What is the higher order Stokes phenomenon? As I mentioned before, I mean, that happens if you go double exponentially small. So you have your normal expansion, you have a re-expansion in terms of hyperdeterminants, and if you do that, then again you can plot just the remainder. And so what we have here is the original function, the first expansion, and the re-expansion, and then we just truncate and just plot the remainder. For the gamma function itself, it's the red curve. And if you see it, then you probably say, okay, that's again an error function. The only difference is that halfway the crossing, the value is not a half, it's 3/8. That's not easy to spot, but if you look very carefully, you see it's not a half. And more weirdly, for the reciprocal gamma function, the error is actually, nothing should be switched on, because there's nothing to be switched on the other side. But you still get this little blip, little hump, and it's not an artifact. The value is 1/8. So weirdly enough, there is a small exponential there for a moment, and then it disappears again. And I guess John will tell more about that in his example in the second part. So I want to understand these values here, the 3/8 and the 1/8. For this particular example, it's actually straightforward because we have some magical formulas. I mean, at the moment that you have, because we have equally spaced points in the Borel plane, and in that case, the second hyperdeterminant, that's the function that mimics that behavior. It has some nice formulas in terms of the first hyperdeterminant. So this function here, the more complicated one that we want to approximate, can be expressed in terms of the first hyperdeterminant, which is just a simple incomplete gamma function. It's a square plus or minus 1 where the entries are doubled in here. And we know what the values of these functions are halfway. They are half. And if you plug them in, then you end up with either 3/8 or minus 1/8. The reason that I write here plus or minus is because, as you will see in a moment, there is a Stokes phenomenon happening that these things are on the branch cut, and you really have to decide whether they are on the left or on the right of it. It's almost like what you deal with, you have to deal with Ekal medianization. You have to decide whether to the left or to the right. But these numbers are exactly the numbers that you saw on the previous page. We actually have formulas to generalize this for this very particular case, that the exponential that is switched on at the nth level, the multiplier is not 3/8, but it's then given in this formula here in terms of Pochhammer symbols. And if you add all those contributions from these exponentials on the Stokes line itself, then you can resum that. It's a resum trend series, and you get this square root of 1 minus e to the power 2 pi I z. If you go through the Stokes phenomenon completely, and you arrive on the other side of the imaginary axis, then the sum is just this same object, but without the square root. That makes sense because you want to switch on all those poles. Those poles arrive on the other side for the gamma function. So this reflection formula shows you that this makes sense, but this actually also does make sense, because if you are on the imaginary axis, then these things are roughly the same, and the product still has to be this sign part here, which is actually what you see there. So both of them do make sense. And it also shows you that these numbers are correct. The 3/8 is what you need, otherwise you would get the wrong formulas there. So they're not half, all of them, but they're these more complicated numbers. Okay, I wanted to skip this slide. On that slide, I was going to explain how you get the hyperdeterminants via the Borel machinery. For the first hyperdeterminant, I'm not going to say all of this on this slide. The main thing, this first hyperdeterminant, let me immediately go to the next slide. It can be approximated with an error function plus correction terms. The proof is actually given here. I'm not going to give any proofs or hardly any proofs for the remainder in this talk. I just wanted to highlight a few details in this proof because it shows you what you can do actually with, and also maybe what the hard part is if you actually generalize it. So this first hyperdeterminant has the integral representation that I mentioned before. It's an exponential, a power, and a pole. On the Stokes phenomena itself, there is a relation between this sigma, the large z, and the number of terms n, which you approximately in this situation. So if you rewrite this integral in this form here, then you have this large capital N there. It appears at two places, but if you have done any asymptotics on gamma functions or so, you know that you just combine them in one exponential, and the exponential will then have a phase function that is this t minus the logarithm of t. Then you can use your Laplace's method to make it a clean saddle, a half s squared, but the price that you pay for it is that you get an extra function which I call f of s. So this is still all exact, which is in terms of the derivatives, the change of variables. But this new function here has a clean saddle. It has a simple pole and an extra bit. This is still exact here. I haven't cheated anywhere. And if you then just take for this f the value at the pole, then you get this function here, which is just an integral with a clean saddle and just a pole and nothing else. And that function is exactly an error function. So this is really just this function here. And the remainder function that we have here, it still has this saddle, but this g will be, because we will be played around with the value at the pole, this function here doesn't have a pole anymore. Its poles are on the different Riemann sheets. It will have poles, but they're on different Riemann sheets. So for this final term here, you can just use simple asymptotics, saddle point asymptotics, and get a complete asymptotic expansion. And the result that you have here is globally uniform. It holds everywhere on one Riemann sheet. But this is possible with simple integrals. Now we're going to encounter double integrals, and then life is much harder. I hardly know any papers where people actually do proper uniform asymptotics for double integrals. So this is the second hyperdeterminant in general. We have magical formulas in the case that the Borel singularities are equally spaced. That is when these numbers here, these two numbers are the same and these two numbers are the same. But in general, you won't have it. So this is a double integral. You see that you have a pole with respect to tau 0, but you also have a pole with respect to tau 0, tau 1. So there are two potential Stokes phenomena possible. The first one looks a lot like the normal Stokes phenomenon, and the second one is new. And actually, when we introduced these functions in the 1990s, we weren't appreciative of that one because we didn't know the higher order Stokes phenomenon, but now it all makes sense. The two Stokes phenomena you can also see with respect to the connection formulas. If you take the connection formula with respect to Z, then you can see that the Stokes phenomenon itself switches on a lower order, a first order hyperdeterminant. And remember, a first order hyperdeterminant deals with a Stokes phenomenon. And the other, this Stokes phenomenon that you see there, that's the higher order Stokes phenomenon. It switches on also a lower order hyperdeterminant, but now it's actually a sum of the two ends, but also more importantly, the sum of two sigma. So potentially you could have an extra singularity in the Borel plane if you had this root. There's one more nice formula that holds in general. That's the one at the bottom. That's with symmetries. If you swap these two columns here, then you can write it as a product of two simple ones. And that's actually a very useful formula. Okay, so I'm now going to do three more things. I deal with the first Stokes phenomena, which was with respect to the Z part, so this pole here. Then I deal with the Stokes phenomena that happens when in between tau 0 and tau 1. And the final result, and that's the most important one, especially if you think about nonlinear problems where maybe the singularities don't move, that is when both happen at the same time. And that was the big, all the work that we really had to do. The first two are very easy to do. For the first one, you can actually use just this formula that I just mentioned here. There might be a Stokes phenomenon between, say, z and sigma 0, but I don't expect that sigma 0 and sigma 1 are very different, so there's no Stokes phenomenon between z and sigma 1. That means that this term here doesn't have a Stokes phenomenon, this term doesn't have a Stokes phenomenon, but this one does. So if I want to understand the Stokes phenomenon of this function here, it's just what happens with this function here, and that's all. So I can just write the Stokes phenomenon and the smoothing just in terms of the smoothing of this function plus extra terms. And that's all I probably want to say about that case. So that one is relatively easy. The second Stokes phenomenon, that's the higher order Stokes phenomenon, but not in the critical case. It's a bit more work. We have a proper double integral. We can actually, we are going to switch on this first hyperdeterminant, and you can actually play around with it. I'm skipping all the details here. The double integral can be written as an extra double integral, which is this remainder term, and a product, and that's just by playing around with the integrands. And this is the object that we want to switch on anyway. This I function here is defined here. You can recognize it maybe as a hypergeometric function, and it actually is going to deal with the Stokes phenomenon, so it's slightly more complicated than what we had before. But if you rewrite it correctly, then you end up with a function that has a simple saddle point, a simple pole. This is the general function here, and those can coalesce. And then again, we have the machinery for that, and that will again give us an error function. The only worrying bit here is actually what about this double integral, because this is an integral of this I function, which was an integral itself. In this particular case, when there is no Stokes phenomenon between sigma 0 and sigma 1, this I function here in that integral is innocent, and you can estimate it, and you see that the only Stokes phenomenon that happens is actually with respect to this first term, and the results are given here. So it's slightly more complicated than in the first case. You still get a nice clean error function. It definitely goes through a half. So I'm plotting here the object that is being switched on and the error function on top of each other, and you see no difference. So again, this is the relatively simple case, but this is really the switching on of the higher order Stokes phenomenon in the simple case. But in the extreme case, then that double integral, that one that I could ignore on the previous page, I can't ignore anymore. It's very messy, and I'm not going to give you any details on that. But that would take probably several hours to explain all the details there. But I'm just going to explain give you the result. The result is also in terms of a new special function. Although you might read error function here, but we have an extra entry there. There's a lambda there. You might see it as an error function of an error function or so, which in a way, if you start thinking about it, probably does make sense, because it's a higher order Stokes phenomenon, and the normal Stokes phenomenon is an error function, and two things happen at the same time, and so this function has to be introduced. It has many properties. So if at the moment that you introduce a new special function, then you probably want to also properly show that it's actually an object that we can control, that we understand, so we need lots of formulas, and they exist. There's a reflection, but here, this is actually more important here. First of all, when I take lambda 0, I just get the error function. When I take lambda as 1, I get a product, and that's the product that we saw before. At some point, I showed you a magical formula for the F2 function in a very special case. This is the special case where you get a product of error functions. But more importantly, actually, for this talk is that if you, at the moment that you take general lambda, that this extra parameter, you take x is 0, then we can actually evaluate the value, and that value is actually important, as you will see in a moment. On the remainder of this and next slides, I'll just give you many more properties. There are asymptotic expansions for these functions. They are not complicated, so you can compute these functions at infinity. There are also Maclaurin-type expansions at the origin, so we can also evaluate it near the origin. As a previous slide, I showed the reflection formulas and things like that. So this function is computable everywhere. So we can use it as a new approximant. Here is the result. I'm not expecting anyone to read any of the details. The general second order hyperdeterminant can be approximated. how bad are the colors? So this is either pink or purple, depending on how good the screen is. The first approximant is a simple first-order hyperdeterminant, similar to one we saw before. Here I have my new error function, so there are 2 entries in here. And the red bit here is also needed to get the correct error estimate, but the red bit is as small, as you will see in a moment. This is a uniform asymptotic expansion, unfortunately in a very narrow region. It's uniform with respect to Z, but the sigmas, they live very close to each other, and they have to be in order of 1 over, the phases cannot change more than 1 over n. And think about n0 and n1 being very similar in size and large. Just to convince you that it actually works, I'm plotting here the functions for an arbitrary case, and the pink function is the one that we want to approximate. That's the one that you can see here. The blue bit is up here, the green bit is down here. If you add them, you get roughly the pink part here, because the big red mess that you can see here is just this thing that's hardly visible, and Z in this case, or the ends are roughly 41, so it's not that large, and the red bit is already very small. This is a picture of the remainder. Actually, this is the remainder after taking away the n1, so all we wanted is to be of order 1, but it's actually going to 0, so it's actually doing even better than expected there. So this machinery works. It doesn't hold in as big a region that I would love it to work. As I was saying, it holds uniform for large sectors of Z, but not with respect to the other phenomenon, but still it works. But more importantly, if you're dealing with nonlinear problems, you don't care about that singularities are moving, but they're definitely all lined up, but maybe not equally spaced, then this is my final slide. Then you want to know how much is switched on of this second exponential. And now the 3 over 8 that you saw before is just written down here. So there is a simple formula for it. That's how much is switched on of the new exponential. If you plug in that n0 is n1 in here, then you will get the minus 1 over 8 that we got for the gamma function, or for any equally distant spaced singularities in the Borel plane. But this is the general formula. And John will now actually start. Oh, actually, one thing I should say. So this is what you get, what the value is in this picture at the hump here on this line. Okay, now John takes over, and somebody will switch us over. Yes. Okay, I'll do that.
Marvelous. I'll probably just click the thing on the computer, but
please do.
Thank you. Okay. So thank you, Adri. My slides are even scruffier than normal because I only got this work in shape I was happy to talk about with it this week, but it does go back years, as Adri's implied, including at KITP. I'm going to talk about 3 PDEs which are recorded there. I regard the second and third as potential toy PDE problems in the sense Phil talked about yesterday. So the second one's a generalization to the first. The third one is a limit case of the second in an obvious sense. So I'm going to start by doing a problem that's well understood by other methods, but it gives me the most obvious physical motivation, but also allows me to explain the machinery in as simple form as possible. So the equation at the top is reaction diffusion equation applied in lots of contexts. So if you think about it as epidemics, the nonlinear term is U is the infected, and then 1 minus U would be the susceptibles. So it's okay for historical epidemics. It would be no good for COVID and stuff because the transport term for COVID isn't diffusive because of aeroplanes. The key phenomenon is this establishment of a traveling wave that takes you from the stable steady state to the unstable one. The question I'm going to try and address is how does the wave speed depend on the initial data? I'll specify initial data in a second. This famously can be dealt with via the linearization, which is recorded there. Throw away the u squared term. The intuition there is in the middle, even though the linear problem will grow exponentially, and that will be cut off by the nonlinearity, the waves are actually dragged by the wave fronts where the solution is small. So by capturing exponentially small terms, I'm going to be able to work out how fast the wave goes. I reduce it to the heat equation at the bottom, which is what I'm going to talk about. But then the wave front is where, in the unfactored form, the solution becomes order 1. So this is how I'm going to prescribe where the wave front lies. Okay, so the appropriate form of initial data to think about is exponentially decaying. So I recorded that at the top. I'm going to want the large time behavior. For this example, I'm going to do it through this intermediate step of introducing an artificial small parameter in the time scaling. Then there's 2 spatial scalings. One's diffusive, one's in effect ballistic. So the diffusive one is the uninteresting one where you just get back to the heat equation. Epsilon's artificial, so it has to scale out of the solution. So it has to depend just on x over t to the half, and you get the famous Gaussian. The hyperbolic scaling brings the epsilon fully into the PDE, so it's now in the form to which you apply the Liouville-Green method, and that's where the exponentially small terms are going to come in. And F then in Liouville-Green satisfies this Hamilton-Jacobi. So right, I go on about this terminology a bit too much. So I put up this slide for 2 reasons. One is to mention that other people state the thing even much more strongly than I do. So Bailey talks about it being ignorant and so on, to call it WKB. But the more important thing is it reminds me to say a few things about Jeffreys. So the thing that is in WKB but not in Liouville-Green is the turning point formulae. But Jeffreys had them a few years earlier. And indeed, they're in his Adams Prize essay of 1922. So we can legitimately say we should be celebrating the centenary of when Jeffreys invented the WKB method. Jeffreys appealed to me even more when I saw this final sentence. So George Green was a Nottingham miller, which is one of the reasons I kind of latch onto this. Okay, so this is from Heading's nice little book on the integral phase integral method. He wrote it when he's at the University of Southampton. Dingle uses the terminology either phase integral or Liouville-Green, depending on context, so that's good enough for me. The other thing to say about the Jeffreys is those of you staying at Eddington have probably noticed there's a student hall of residence called the Swirls Court. So Bertha Swirls was Jeffreys' wife. They co-wrote Jeffreys and Jeffreys, which was the set text on mathematical methods in physics when I was an undergraduate. I suspect it's rather little used now. I'd be interested to know. But Bertha did show up at the 1995 program, and I'm told she was very active and formidable at that point. She died in 1999, so at the time of that program, there was a living link with the prehistory of this stuff. Okay, back to the problem. So there's my Hamilton-Jacobi at the end there. Again, because epsilon is small, is artificial, the thing's got to depend only on x over t. So you reduce it to an ODE, which is Clara's equation, as it always is in this kind of context. If you remember how to solve Clara, you differentiate with respect to zeta, which is a slightly odd thing to do, but then factorizes into the 2 different classes of solution. So E is the envelope solution, the one on the left, and I can keep labeling it as E. F is the solution that comes from my exponential initial data. So I'm going to call that I throughout. So one of the issues with PDEs, so with ODEs, you always know at the beginning how many exponentials there are going to be, and indeed what form they take. With PDEs, you don't. So the first task is to establish how many you need to worry about. So that's one significant extra complication. Okay, do the usual next step in Liouville-Green to get the amplitude equation. That's recorded at the bottom, and the solutions corresponding to the 2 different forms of F are recorded at the end. Okay, so that's the second extra complication for PDEs I'm going to flag beyond the high order thing. So the A's here depend on, these things are the things that can get turned on, right? But these A's are arbitrary functions. So the Stokes multipliers in it, because it's a 2D PDE, 1 plus 1, the Stokes multipliers are functions of a single combination of variables, not just constants. Okay, the other thing you need to keep track of is not just the similarity reduction, but what the characteristics of the original Hamilton-Jacobi equation do. So the key Clairaut equation is the one for how x evolves with time. So that's recorded there. And the two classes of solution, the rays are, of course, straight lines, but one of them is an expansion fan, and the others are parallel straight lines. So that's the picture. So the key thing to observe here is the green rays are the ones that come out of the initial data, but they don't occupy all space, right? There's a final left-hand green ray, and that's going to prove crucial. The envelope ones are the expansion fans, which do exist everywhere. So the question is, there is a Stokes phenomenon going on in terms of how the green rays are switched off, but you don't have to need to know about resurgence and stuff to do this problem. And the reason for that is that the thing on the real line, the thing gets turned off at a turning point, so you don't need to go into the complex plane. I'll come back to that shortly. So the two exponentials, and remember with these pictures, we've got e to the minus f over epsilon, so the larger exponential is always the one at the bottom. So the green one's from the initial data, the red one's the envelope. They naturally, because it is an envelope, they meet tangentially. But the thing that's dominant everywhere on the real line is the green one. And incidentally, the green one I'm going to take to have a single term. It truncates. It won't turn anything on to keep things simple. So the turning point problem you work through, the first two terms in the local expansion of f in both cases are identical, which is why it is a turning point. So it tells you how to rescale everything to describe the turning point on the real axis. And it's error function, so not Stokes smoothing, but in some sense related. So incidentally, you go through this machinery for the heat equation, you get the heat equation back again, so there's a flavor of resurgence going on here, but I'm not going to go into that. So the Stokes lines, by the usual recipe, given by the formula at the top, so they're lines, straight line parallel to the imaginary axis. It moves with a characteristic velocity. That's actually not quite the right intuition, although we'll find the turning point always moves with the characteristic velocity. So this is the structure, envelope, only the envelope to the left switches on the initial data exponential as you cross the Stokes line. Okay, so wave speed selection, if you recall my recipe at the beginning, I want to know where the exponential is, where capital F is minus mu. And that's going to depend where the wave speed sits. If it's to the left, it has to be one of the red rays. If it's to the right, the green rays dominate. So you get a well-known formula for the wave speed as a function of that parameter lambda, which switches as the picture at the bottom implies. So well-known, but I've done it in a slightly different way. And it's not yet got any connection with Adri's talk. I will be coming to that. I know I will repeatedly draw this kind of picture for each of the three PDEs I'm talking about. So if you're a standard applied mathematician, you just do the thing at the top. You'd crunch through the turning point in the real line and come out on the other side. If you want to avoid the complexity of the turning point, you loop round in the complex plane and come to the same answer. One simple general, that's exponential asymptotics, but you don't have to worry about divergent series in terms of the top picture. To do a simple generalization where you do, which is a genuine Stokes phenomenon example, you make the initial data oscillatory as well as exponentially decaying. So the relevant formulae that are there for the turning point, Stokes line, anti-Stokes line. The picture is the important thing, which just lifts up where the turning point is from the previous one. So now on the real line, there's a genuine Stokes phenomenon. The turning point isn't there, but the Stokes line does cross it. To the left of the Stokes line, there aren't any oscillations at all. Immediately to the right, they're present, but subdominant to the envelope. And beyond the anti-Stokes line, they're dominant. So I view this in terms of a quote from Lemmy from Motorhead. So the oscillations are born at are born to lose at the Stokes line, but then come to live to win at the anti-Stokes line. I think Lemmy was quite good on the Stokes phenomenon. Right, so the generalization I mentioned at the beginning is the classic extended Fisher-Kolmogorov equation is the one with the fourth spatial derivative rather than the mixed derivative as the regularizing term, but this is the one I'm going to do. So I do the same thing, factor out the exponential and then rescale to get the thing in the box. I'm not going to introduce the artificial small parameter anymore because I now know how to do everything. So there's Liouville green, there's the Hamilton-Jacobi equation, here's the Clairaut equation, here's the general solution to the Clairaut equation. Ray velocity recorded there, Clairaut solution recorded there. So this is one of these examples where you have to keep careful account of how many exponentials you might have to worry about. So we know there's one from the initial data. In this case, there are 4 more because this equation for capital P in terms of zeta is a quartic. 2 of them are relevant on the real axis because they're exponentially decaying, and the details recorded at the bottom. 2 of them aren't because they're exponentially and oscillatory growing on the real axis. So they better not feature in a consistent Stokes line scenario. Okay, so do the turning point calculation. So again, you factor out the thing from the initial data, you move at the characteristic velocity, and you get the long equation near the bottom. So incidentally, I didn't say this earlier, I do regard turning point calculations as a degenerate case of Liouville green, right? You've got repeated roots, so you get a second order amplitude equation instead of a first order. And you're seeing it again here, right? So Z scales with t to the half in the turning point. So the big bracket at the end terms are negligible compared to the 2 you keep, and you get this formula at the bottom. So the really important thing about that, and the reason this example is interesting, is that it can swap sign. If lambda is less than 1, it can behave like the heat equation, and I'll do that in a second. This thing's positive. If lambda's bigger than 1, you've got backward diffusion, which is seriously ill-posed. So something quite odd must happen in that case. Okay, so I'm not going to do that in detail because you can't write capital F down in closed form and the algebra will get very messy. I'm going to do the telegraph case, which has all the same structure. So the transition occurs at lambda equals 1 here. So I'm going to look close to lambda equals 1. Lambda is plus or minus epsilon. The transformation that gets me to the third equation on my first slide is recorded there. Step 1 is exact. The reason that transformation is interesting and worthwhile is the 2 of the terms cancel, as I've done. So the limit epsilon goes to 0 is this telegraph equation. I'm going to do it as this initial boundary value problem. Okay, so Hamilton-Jacobi is simpler than in the pseudoparabolic case, and I can write down the answer. You lose the 2 roots you don't want by going to this limit case, but it does retain all the structure you do want. So there are 2 envelope solutions because there's a square root when you do the Clairaut business, and then my usual thing from the initial data where lambda is going to be plus or minus 1. The phase velocity is 1 over 2 lambda squared, so the phase velocity is the same both sides of this critical transition. Turning point scaling is recorded at the bottom, and this checks your algebra. Backward heat equation for lambda equals -1, which corresponds to the forward case on the previous slides, and backward for lambda equals +1. Okay, so lambda equals -1. I nearly didn't write the minus, so that's slightly hard to read. It turns out to be quite simple. So the thing I should have emphasized on the previous slide is these 3 exponentials are all real on the real axis. So it's in Adri's kind of scenario, you've got multiple coincident Stokes lines. For lambda equals -1, things are simple because the biggest one is the initial condition one, and that's not turning anything on. So the only turning on that's going to occur on the real line, apart from the turning point, is the negative sign exponential will turn on the positive sign. So, but you do need to check what's going on with how the negative exponential turns on the initial data. In the similar scenario we saw for the heat equation, the Stokes line that does that is now geometrically more complicated. It's not a straight line as this is parabolic as the formula at the bottom. Okay, so the turning point does move with the characteristic velocity. The rest of the Stokes line doesn't, so the heat equation was misleading in that sense. But this again goes through how you might try and go from left to right on the real line and then in the complex plane. So on the real line, you start with E minus to the left. it happens that there's zero contribution to E plus there. So until you look at the complex plane, you don't actually care about E plus at all. The turning point structure is the complementary error function again, which turns on the initial data. So that scenario is very similar to the heat equation. The complex plane picture is slightly more complicated because you've got E minus turning on E plus. But in other respects, it's closely related, but the most relevant Stokes line, the parabolic one, is now curved. Now I finally get on to the stuff relating to what Adri talked about. So it's a minor tweak to the setup, but completely changes the structure. And the way you can see you've changed the structure is this picture at the top. So you switched where the green curve is. So now it's the most subdominant one. Dominates there, subdominant to the other two here. So the turning point is with the envelope exponential that is itself subdominant, the E plus rather than the E minus. Do I need to say anything else about this slide? Right, so on the real line, we have got these coincident Stokes lines. E minus turns on both of the smaller ones. E plus is the middle one, so turns on the smallest. Okay, so the tails are familiar ones. So incidentally, when you extract the equation for the singulant, which determines these tails, it's a slightly different form from what I'm used to. It is a full ODE rather than the equation for chi dash. But if you're a bit cunning, you can solve it and you get these forms, which are the ones you need. So the relevant contributions to the tails. So E minus is turning on both of the others, and it does it through these things in the tail. And the reason I'm recording these will become clearer in a minute. So that the I it's turning on is a constant multiple of I, so the capital lambdas are constants. Okay, so those are the tails of E minus, and they'll interact through the high order Stokes phenomenon that I come to shortly. There's the tail for E plus, which will also be relevant. Okay, so firstly, check where the high order Stokes line has to be. Once you've got a bit of practice in this, you know in advance it's going to be the real axis again, because that's where all the others are. But the recipe to do it is recorded here. So the recipe for the standard Stokes phenomenon has epsilon as the small parameter, takes the quantities in the exponentials to have the same imaginary part. Now the small parameter is 1 over n is the way to think about the high order Stokes phenomenon, because it's the way the terms in the tail interact. So we've got these powers, things raised to the power n on the denominators there. So I write them as exponentials of minus n times the relevant quantities. So the recipe for the Stokes line equates the two imaginary parts as recorded there, which confirms it's again the real line. Okay, so within the tail of the dominant exponential, the thing that switches on the middle exponential can switch on or off the thing that switches on the smallest exponential. And we come to the relevance of that in a minute. Okay, so I am nearly done. So I should say that there are things that need finishing off here. I have done the smoothing of the high order Stokes phenomenon in a similar style to Adri, though of course far, far less rigorously. But it actually made me believe in hyperdeterminants, which I didn't before. I haven't implemented that in this special case, and there are some special features of this, so there's more to be done. And also there's a key issue, the turning point, which needs sorting. But let me go through the Stokes phenomena that are happening and then come to what it tells you about the final conclusion and how you select where the exponential is present, the lambda term. So the top picture is going from below the real axis, on the real axis, above the real axis. So how E minus turns on E plus is completely standard. There's minus I of it on one side up to some multiple plus I above it. Next, how E plus turns on I. How E plus turns on I. So the middle exponential, which is being turned on across the real axis by this top picture. So this is non-standard. Right, I've just written minus I and plus I there, but really these factors are themselves Stokes smoothings in the way Adri's alluded to. But kind of the parity, I think, works that it's minus below and plus above. So you go from 0 to some finite multiple and back to 0 again, which is the blip thing that Adri alluded to. Right, the high-order Stokes phenomenon has to be different either side of the turning point in terms of the sign, and this is the thing that caused me a bit of grief. Right, so because of these halves in these various gamma to the n plus half and things, there's various square roots sitting around, and you need to be careful about which ones apply. And I believe that's the root of this switch in sign either side of the turning point. But as implied, there are some things I still want to go back and understand better. So within the tail, it is the standard higher order Stokes phenomenon. E plus is present everywhere in the tail because it's the larger of the two contributions from the tail. It dominates I. So to the left of the turning point, you go up to signs and things, minus I, 0, I, as you cross the Stokes line. On the other side, the opposite. Okay, so that's what's happening in the tail. So on the Stokes line itself, the I contribution is absent, but either side of it is present but with opposite signs. So that constructs what's going on in the tail, and then once you know what's in the tail, you can work out what's being switched on. Right? So the switching is being done by within the tail of E minus, so I've used purple to indicate something slightly different in this picture. This is the thing in the tail that switches on I is itself the I contribution to the tail. And that's got this blip kind of phenomenon, but with opposite signs. So the reason I've harked on about the need for the difference in sign either side of the turning point is you expect the initial condition exponential to be present only to the right of it. But this situation has it being switched on everywhere across the high order Stokes line, across the Stokes line. But the implications of the high order effect are on one side of the turning point, that gets cancelled back down again by the higher order Stokes phenomenon, whereas the other side it gets doubled up. So that's my conjecture. And this, I think, is the final picture. So this is, again, how the connection problem works, and you can't do this just by looking at the real line because of the way the turning points work. But that's, for the record, what the real line would look like. But then, more importantly, the complex line and the various things going on. So I believe the exponential, which might be selecting the wave speed, but wouldn't be in this example, is present only within the Stokes line. So the shaded region close to the axis to the right of the turning point. As you go across that combined Stokes line, high order Stokes line, it would take the form of the blip. The only other thing that's going on is the more conventional Stokes phenomenon of E minus turning on E plus across the real axis. So what else to say? There's a couple of quick conclusions at the bottom, but one of the things I haven't said yet is this isn't a pathological example. In lots of PDEs, you would get this scenario where there are multiple exponentials that are real on the real axis, and something like this may therefore happen. All the above contributions matter, so the gory details I subjected you to a second ago do all come into play. To get this picture in a consistent way, you do need both the Stokes line effects and the higher order ones. And then finally, the thing I haven't properly resolved is the business about the turning point. So there's a turning point between E plus and I on the real axis. In the same place, there's a turning point between the contributions to the tail of E plus involving the same things. So neither of those, I haven't resolved either of them yet. This will be the easier one. This will be harder, unsurprisingly, because it's higher order. So this is a turning point sitting within a Stokes line. And that's kind of implicit in the very odd structure of what's going on if you just try and track things along the real axis. So you get, if you're trying to track from left to right, you're thinking about having to solve the backward heat equation, which is telling you you're in serious trouble. It's very ill-posed, so I do find this thing quite weird. So but it's not just the heat equation. It'll be the heat equation driven by exponentially small terms from the tail of E minus. And there must be some kind of magical thing where they're of exactly the right form that the ill-posedness of this backward heat equation doesn't matter, and you get back to a sensible thing beyond the turning point. Okay, and I am done pretty much on time, so thank you, Tom.
Thanks, John and Adri. So, questions, comments?
So some of this analysis you went to the third equation that you wrote, but what I didn't grasp was how does give you the information, where is the information now about the issues that you were having with the second equation?
So fortunately, so to be clear, I haven't done the second order, the second problem properly, but I'm near enough convinced it's going to be the same. So the derivation of the third one from the second is recorded here. But the thing that's telling you it's the right thing to do is, you know, from the quick analysis I did of the second PDE, the third order one, which of the exponentials matter. This checks that the limit case of those exponentials are all retained in this lower order problem. So I believe the structure, at least sufficiently, and indeed I know only sufficiently close to the real axis, is the same as it is for this one.
Okay, thank you.
So do you have enough information now to get the wave speed in the second problem, or is still more to do?
Yeah, so, I mean, unfortunately, the most interesting case where lambda is bigger than 1, the exponential never determines the wave speed, so it's just determined by where this capital F goes through 0. In the case where lambda is less than 1, so unsurprisingly, it's slower decaying, is more likely to drag a wave faster. You can go through the same kind of calculations I did for the heat equation.
Yeah. Is any of this analysis feasible in 2 spatial dimensions?
There's no reason why not. I mean, the radially symmetric case, the leading order Liouville green, is the same as for 1D. If circular patterns destabilize, the whole situation becomes much harder. I can see in principle no blocks, but the calculations will be much more complicated.
Is it just more messy, or is there a fundamental difference?
So if it evolves to radially symmetric, I don't actually even think it would be much messier. In the cases where it doesn't, it would be substantially messier, but I don't think fundamentally different.
Okay. Thanks.
So it's a rather more general question. So you got away doing PDE by only complexifying X, essentially, and keeping T real. Is that a strategy that we could use in general, or does it matter that it's first order in T, for example?
I suspect it does. I mean, the wave problems, it's entirely unclear which one you complexify, because it's symmetric in X and T. I do wonder about whether complexifying T gives you something extra. So the stuff we're doing with Andre at the moment about blow-up, complexifying T does help, because it gets you around the singularity, which is present in the complex, in the analytic continuation in X. So I don't have I'm always aware of that question. I don't have a terribly satisfactory answer. There is something about causality. So it's causal in T, it's not in X.
But it may be in general that you want to complexify them one at once rather than both together.
Yeah, I mean, I can't think in more than one dimension, so I'm already in trouble. Yep.
In the beginning, you mentioned the interpretation in, unfortunately, a not coronavirus applicable disease propagation mechanism. So is there an interpretation of the Stokes phenomenon for such a disease?
I've no idea. So, I mean, the people who do the simplest transport models for epidemics that reflect aeroplanes and things will put levy flights and things on the fusion term. So I am interested in thinking about these problems in a non-local context, which Fatih is thinking about at the moment, in fact. But we're nowhere near the level of complexity you'd need for this. Yeah. It would be, yeah.
Anybody else? Okay, let's thank Adri and John again.
Thank you.